Hello, everyone. Welcome back. So, we're going to wrap up our discussion of pretty much the last topic. We'll cover liquids, solids, and intermolecular forces. So, we won't talk much about solids because we don't have time, but basically, everything I cover will go over why some things are solids and why some things are not solids, and why some things are predominantly liquids on the basis of their what we call IMFs or intermolecular forces. Okay, so this chapter is pretty important, so we're going to take our time here. And if we have time, we'll go over chapter 13. But I don't want to rush that chapter, so we might not get to it. So I might cut some of my lectures short, just because it's remote, so we kind of go at the pace of the quarter here, of the semester here. Okay. So let's talk about intermolecular forces, but first let's revisit the structure of gases, liquids, and solids. So if we take a screenshot of a gas, like in this picture below, we can see that at any given time, the molecules, these little dots here, are widely spaced. So they're kind of like if we took a snapshot and we saw a picture of these molecules, they won't be next to each other or kind of congregating. They'll be kind of widely separated, just like we saw in chapter 5. They're constantly in motion. They have really no influence on each other. Their intermolecular forces are weak because they're moving so fast, so it overcomes those attractive forces. And there's no significant intermolecular, like I just said, there's no really attractive forces because they're moving freely and independently of each other. Now, we talk about liquid, that's a little bit different. A liquid, so you take a snapshot of a liquid. Just imagine that these molecules are vibrating in space. So liquid molecules are allowed to flow, so they do have space in between them, but they kind of move together like a unit. So it's a cohesive action here. So the IMFs or intermolecular forces are strong enough to hold the molecules together. So that's why when the molecules move, they don't move as individual particles. They move together as the bulk liquid. The molecules can slide over one another. That's what gives liquids their unique properties. They can slide and fill the shape of their container, etc. So the best way to think about this is imagine a bag of marbles, and you're shaking them vigorously back and forth, right? The marbles can slide over one another, make some sounds, and they assume the size of their container. So that's what a liquid is. They're more dense than gases, but less compressible. So it's harder to compress a liquid, just because the liquids, they kind of move together as one. Okay, now let's talk about solids. Solids, you see here, there's really no visible space between the liquid, between the particles, and they're fixed in place. So we say they kind of vibrate in motion here. So they're still in motion, right? They still have kinetic energy, but they're vibrating. So the intermolecular forces, they're strong enough. So in this case, they're strong enough to keep the particles in a relatively fixed position to one another. So there's no way that solids can be compressed, and that's because of the lack of space between the molecules themselves. All right. Hold that thought, and then I'll be right back here. Let me just do something really quick here. I'll be right back. Okay, let's see. All right. Okay. I'll be right back. Give me one sec. All right, sorry about that. Okay, so now let's talk about. So we can look at how compact things are by comparing densities of solids, liquids, and gases. And we see here as a solid, the density is much higher than the liquid, or I mean, much higher than the gas. But compared to the liquid and solid, they're not very much different, and that has to do with how well it packs in the liquid and solid state. Okay, so if we think about this kind of idea here, what can we say about why are the motions different in the three types of matter? Well, we can say that our answer is based on the intermolecular forces. Okay, so these kind of interactions between matter, they're governed by the strength of these intermolecular forces, and that's going to be the highlight of this chapter. Okay, so let's go over some terms here. Okay, so intramolecular bonds or forces, the prefix intra comes from, it means within or inside. So think about, like, you know, in school, if you played intramural sports, those are sports between teams formed in the same institution. So when we refer to covalent bonds, we call them intramolecular forces. And these are the chemical bonds that are formed between two atoms. So we call them chemical bonds, okay? So that's intramolecular. So when you think of intramolecular, think actual chemical bonds. Don't think intermolecular forces. Now, you know when we have water, right? Water usually, you can't actually see the individual atoms, but you can see water droplets, and if you add two droplets close to another, they kind of combine to form a bigger puddle or bigger droplet, right? And that's due to the attractive forces water molecules exhibit, and those are called intermolecular forces. So intermolecular means between. So think of like interact, intermediate, something that connects two things, international, and intercollegiate. So think of intermolecular forces are the attractive forces that kind of attract more molecules to more molecules. It has nothing to do with the attraction between atoms, okay? So that's the difference. So we want to be sure we understand this difference because probably on the exam I'll test vocabulary, okay? To make things a little bit more fair in case, you know, there's we didn't do there was it wasn't you didn't students didn't have or didn't do too well on the free response. I'll try to mix it up a bit. Okay, all right, so let's look at the water molecule. So we can really define these two forces by the strength of such forces by comparing the bond energies and the energies it required to break the intermolecular forces. So let's look at this diagram here. So imagine this water molecule here. We see the attractive forces here between the dotted lines, and the single bond bolded line, or the line that's not dashed, that's the actual chemical bond. So let's evaluate them here. So it takes 463 kilojoules to break the HO bond. Okay, so let's just annotate that right here. So we're going to say this is roughly 463 kilojoules. Okay, so that's a lot of energy. So that bond is 463 kilojoules. However, to break this intermolecular force, it only takes 45. So see, there's a big difference here. But this is also why it takes a lot of energy to boil a lot of water. And that's because it actually takes some energy to separate the molecules to the gas state. Okay? So you see the vast difference here, and that makes sense because if we're breaking an OH bond, we're destroying the water molecule. But if we're breaking up the intermolecular forces, we're simply going to a state change. So from liquid to gas. Okay? All right, so make sure we can understand this difference here. Intermolecular force the dotted lines between water molecules, and intramolecular bond or force for the actual chemical bond between atoms in water. Okay? All right. So what happens when temperature increases? Well, let's use water as an example. When the kinetic energy of a sample increases, as the temperature increases, remember they're directly proportional, the blank motion that occurs disrupts the intermolecular forces between water molecules. So when that happens, remember our motion increases, so we're going to have increased motion. Okay? All right, let's use the water example. As solid water becomes ice, it gets warmer, right? The kinetic energy of the water molecules eventually becomes too blank to allow the molecules to be locked into rigid structure of ice. So in this case, the water molecules eventually get enough energy that it becomes so large that it can no longer stay in the structure of ice because the water molecules want to break free. Okay? The solid then melts to form liquid water, right? The intermolecular forces are therefore, we say, weakened because they're no longer holding the water molecules together in ice, so they're being disrupted to allow the molecules move throughout the liquid. Okay. Now, as the temperature continues to increase, the kinetic energy of the water becomes so blank. And the molecules move blank that most of the attractive forces are overcome or disrupted. So it becomes so large now that the molecules move rapidly. And we go from the liquid state to the gas state, where now each particle moves randomly, so it's no longer in a fixed position. It no longer has a fixed volume. It's going to move randomly, and the increased motion is. However, the increased motion is it sufficient to overcome the strength of the covalent bonds? So do we have enough energy to break the chemical bonds that hold the atoms together? We're going to say no. So insufficient. So when we go to the gas state, that's not enough energy to convert water into its elements. So it's not enough to break the bonds here. Okay. Hopefully that was okay. All right. So now let's think of low temperatures. At low temperatures, molecules have less or more kinetic energy to overcome the attractive forces. So we're going to say they have less energy, right? Because they don't have, they're not moving as fast because of temperature. And hence they approach each other more closely or distance themselves from another. If they're not have enough kinetic energy, they're not going to move as fast. So they're going to kind of stay closer together here, just like in a solid. Okay? So then at higher temperatures, the molecules possess sufficient kinetic energy to allow for a blank separation or closer interaction. And in this case, they will have larger separation, as we saw for the gas molecules. Okay? All right, hopefully that was all right. Let's move on now. Okay, so let's talk about the factors that affect intermolecular forces. Okay? So then thinking about intermolecular forces, you kind of have to think conceptually about these molecules, and you can kind of relate it back to things you see in real life. Like if you give something enough energy, you're going to, obliterate something, right? Just like if you heat something too hot, you're going to eventually cause things to expand or form gases, expand, and then disappear into the atmosphere. So you could kind of relate this to many things you see in daily, all right? So let's talk about the factors. The distance between molecules, as temperature increases, the distance between molecules increase. The further the molecules are from each other, the weaker the forces. As we see from Coulomb's law, force equals charge 1, charge 2, divided by radius squared. So the size and shape of molecules also affect the intermolecular forces. We'll go into that. So the further away you are, and the size and shape will play a big role. So to kind of summarize here, so the difference between these three states of matter is based on the competition between the strength of their intermolecular forces, where gases are the weakest, have the weakest forces, and solids have the strongest. So when the force of attraction between the particles is relatively weak, we say the substance is likely to be a gas. So a gas at room temperature. Okay? When the force of attraction is strong, the substance is more likely to be a solid. And then lastly, when the force of attraction is kind of just right, not too strong or too weak, we say it's likely to be a liquid. So as chemists, we like to handle solids, preferably when we're doing a reaction. But sometimes they're liquids, and that's okay. The thing we don't like is when things are gases, because they're really hard to handle, and they're hard to measure out. Like on a balance, you can't really measure that. So gases are a pain. Unless you're doing industrial chemistry, we don't like to work with gases. They're hard to control, and that's because they have basically no intermolecular forces. Okay, so now let's talk about the kinds of intermolecular forces. And now this is the topic that I think has one of the most important parts of general chemistry, because if you go on in other chemistry, especially organic, you'll need to be able to recognize the kinds of forces molecules have and how that plays a role in their properties and reactivity in some ways. Okay, so let's go over that. So remember, we're calling chapter 5 in gases, based on the kinetic theory of gases. There's assumption that in gases there's no force of attractions between particles in the gas. However, there's one key issue with that. If this were true, gases would never condense to form liquids, okay? Or in solids at low temperatures. So the fact that helium forms a liquid at a very, very low temperature kind of disputes this fact, okay? So recall that, remember, this is not Van der Waals, it's Van der Waals, sorry. It should be Van der Waals. Remember the Van der Waals equation. So the Dutch physicist Johannes van der Waal. Remember, he derived an equation that corrected for the attractive forces between gas particles, but also for the it also corrected for the volume of the gas particles. Okay. So this weak force that's present between gases and liquids and solids, we call them Van der Waals forces. So we can divide these forces into 4 categories. So these forces are intermolecular forces. The attractive forces, we have 4 categories: dipole, dipole, dipole-induced dipole, induced dipole, induced dipole, and hydrogen bonding. So those are kind of the ones you'll need to know. We'll go over some more, but they won't be as covered as much, I would say, but we'll do a worksheet next week in discussion, so we'll talk more about this. All right, so let's stop the video there, and I'll pick this up in the next one, okay? I'll see everyone then.